There's going to be a lecture today, of course, tomorrow, Monday and Tuesday. Right? Monday and Tuesday, yes. Because Monday is going to follow the Friday schedule and Tuesday is going to follow some other schedule. So there are going to be 4 lectures, including today's. And in these 4 lectures, we're going to look at quantum technologies, certain quantum devices. And it's very important that you pay special attention to these lectures because the topics that I'm going to cover, they are sputtered in different areas, in different books, and so there is no one consolidated account that you will find for all of these technologies that I'm going to cover. So you really have to pay special attention and you must attend the classes. And there is no chance for a homework on these topics. So you really have to work hard on this. There's going to be a quiz on Monday or Tuesday, by the way, the last quiz. Alright, so what I'm going to address now is, I'm going to see how what we've been discussing, the science of quantum mechanics, how quantum science is converted to quantum technologies. So what we've been thinking about, wave functions, tunneling, we consider these to be just figments of our imagination, but that's not correct, because there are tangible devices, there are tangible phenomena that are based upon tunneling, and I can go to the length of saying that we exist because of tunneling. Either we look at the mutations in our genetic codes, or we look at the way the sun produces its energy through radioactivity, alpha decay. And alpha decay can only be explained through tunneling. So one of the greatest triumphs of quantum mechanics greatest successes of quantum mechanics is the explanation of radioactivity. Okay, just a minute please. ऐसा करना थोड़ा सा ऐसा करना चलिए. So one of the greatest successes of quantum mechanics is the explanation of radioactivity. Now let's start our discussion of radioactivity. Suppose I have a mountain and there is a person standing on this side of the mountain and there is a person standing on the other side, and this mountain has a height such that if an object is placed on the top of the mountain, then it will have a potential energy equal to 1000 joules. Now this person, I call him or her A, and this is B. A has a cricket ball with him, and A issues the ball with enough energy so that it overcomes this barrier, reaches the top of the hill, and this ball falls down and reaches B. And B measures the energy of this ball. Alright, so what is the minimum energy? Now B knows that this ball has been issued from the other side of the mountain. What is the minimum energy B should measure of this ball? What is the minimum energy that this ball must possess if everything has to make sense? बिल्कुल आप एंड पे बैठिए, आप बताएं. Why 1000 joules? जी Why 1000 joules? Well, this is the correct answer, but you need to explain to me what this means. Anyone from that row, from the second last row?
Is 1000 joules the potential energy? So if it is at least some kinetic energy, it means it should be somewhere less than 1000.
So this energy should be somewhat less than 1000 joules?
If the ball has some kinetic energy.
If the ball has some kinetic energy, it must have a minimum energy of 1000 joules. The kinetic energy could be larger. So which means that the energy of this ball has to be at least 1000 joules. It could be larger than 1000 joules. Okay? Because when the ball has come down, all of its potential energy has been converted into kinetic energy. And here the potential energy is 0. So B measures the kinetic energy of this ball, and this kinetic energy has to be at least 1000 joules, because all of this kinetic energy is coming from the potential energy. Here the potential energy has gone away, it's faded away and given rise to kinetic energy. So the kinetic energy has to be at least 1000 joules here. So this energy has to be greater than 1000 joules. Okay, this makes classical sense. Alright? Now what B observes is that the energy of this ball, which is wholly solely kinetic energy, because the potential energy here is 0, is say 800 joules. Now is this classically possible? No, it's not possible, because if the kinetic energy here of this ball as measured by person B is 800 joules, then it means that the kinetic energy at the top of the mountain should be minus 200 joules, which looks like nonsense. Ignore friction. Why do you go into the technicalities of ignore friction? Alright? So if this person B observes the energy to be 800 joules, there's something glaringly wrong. But this effect is observed in our daily lives because tunneling works. Even if this cricket ball had an energy of 800 joules, which is insufficient to surmount the 1000 joules potential barrier, this ball can somehow tunnel through this obstacle with its 800 joules of energy and reach the other side. And this effect is observed in what is called radioactivity. Now what happens in radioactivity? Suppose I have a nucleus of uranium. Its atomic number is 92, say 234, the mass number 234. I'm talking about the isotope 234. It has 92 protons and the remainder, they are neutrons. Now this is a positively charged nucleus because it has 92 protons. So what happens is that this nucleus decays. Okay? And when this nucleus, which is called a parent nucleus, decays, it gives rise to another nucleus. And that nucleus is thorium. with atomic number 90 and mass number 230. And of course the number of protons and the number of neutrons has to be conserved. So in the process a particle is emitted, and that particle is a combination of 2 protons and 2 neutrons, and it's called an alpha particle. And this alpha particle, since it has 2 protons, it's similar to a nucleus of helium. So this is an alpha particle. This is the daughter nucleus. So what's happening here is I have a parent nucleus which has 92 protons and a large number of neutrons, and for some reason this parent nucleus decays. It gives me a daughter nucleus which is thorium, which has 90 protons and the remainder are neutrons, and a smaller particle is also produced which has 2 protons and 2 neutrons. This is an alpha particle, and this alpha particle moves away with some energy, with some kinetic energy, typically of the order of 5 mega electron volts. This is an alpha particle, and this process is a particular kind of radioactivity. It's naturally occurring. It's not man-made. It's naturally occurring, and this particular kind of radioactivity is called alpha decay. This is the parent nucleus. This is the daughter nucleus. And these typical energies are of the order of 5 mega electron volts. Alright. Now this example is exactly analogous to this example, and I'm going to show you how. Now, is this particle, the alpha particle, charged? Is this a charged particle? Yes, it is. Is this nucleus charged? आप बताओ, yellow t-shirt में, is the nucleus charged? Is the daughter nucleus charged? Why? In order to? But both of them have positive charge, don't they? आप बताओ, साथ आप मुस्तफा के साथ जो बैठे, is the daughter nucleus charged? It should be charged. Why should it be charged? Because every nucleus is charged. It has protons. Protons are charged particles, and neutrons are neutral particles. Every nucleus has to be charged. And is it positively charged? Yes. And what about the alpha particle? Is the alpha particle charged? Positively charged. So both of these species, the daughter nucleus as well as the alpha particle, they are positively charged, and they are repelling one another. And this is the kinetic energy of the issued alpha particle. Now suppose I make a plot between distance from the center of the nucleus and the potential energy VR. And we're talking about a thorium nucleus which is positively charged. It has 90 protons, and we're talking about an alpha particle which is also positively charged with 2 protons. Now both of these are charged particles. Now what we would like to see is, if the alpha particle is brought close to the thorium nucleus, what happens to its potential energy? If I decrease R, what's going to happen to the potential energy? Increase. Because the potential energy is simply given by 1 over 4 pi epsilon naught Q1 Q2 over R, right? This is the expression for the potential energy. So as R decreases, the potential energy goes up. Because now the alpha particle is being brought close to the thorium nucleus. So if the alpha particle is still a part of the nucleus, the potential energy should be really high. Okay? Agreed? If R is very small, which means that the parent nucleus has not yet decayed, then the alpha particle that resides inside the nucleus must have a very high potential energy. Okay? Now what keeps the nucleus intact? Nature does not like high energies. Nature would like to go to lower energies. So this means that no nucleus can ever exist, because if you put two protons together, as you do in a helium nucleus, you put 3 protons together as you would do in a lithium nucleus, 4 protons together as in a beryllium nucleus, and so on. Now these protons are positively charged and you're squeezing the protons closer and closer together. That should not be allowed, because that increases the potential energy. This is a highly unfavorable situation. So what keeps these protons together and what keeps the nucleus stable? How do we account for the stability of nuclei? So in the 1930s, a theory was proposed which stated that when protons are brought close together, their repulsive force is overcome by an attractive force. At very small values of R, at very short distances, the repulsive force between positively charged particles is overwhelmed by an attractive force. So there is a switch over from repulsion to attraction at very small distances. And the potential energy starts to drop, because at these small distances the repulsive force is overcome by an attractive force. So this repulsive force is electrostatic in nature, because it's between charged particles. It's just the Coulombic force. But when R is very small, there is an attractive force that overcomes the repulsive force, and that attractive force cannot be electrostatic, because electrostatics says that positive charges must repel one another. So the origin of this force is due to quantum electrodynamics, and it's a force that exists between quarks, and it's called strong nuclear force. So this strong nuclear force is a short range force. Electrostatics is a long range force. So if a charged particle exists on Earth, it will exert an electrostatic force on a particle, on a charged particle on the moon. It's a very long range force, although the strength is going to decrease quadratically, but it's long range. But the nuclear force, the strong nuclear force, is a short range force. So now what's happening is that we have an alpha particle with 2 protons and 2 neutrons that is sitting inside the nucleus, and it is bound to the large thorium nucleus with the help of these strong nuclear forces. Okay? Because it is the strong nuclear force that holds this positively charged alpha nucleus to the thorium nucleus. In fact, it's a strong nuclear force that why a single proton can ever exist. Because a proton is like a positively charged particle. if you have a positively charged particle, so if I draw a diagram of a very simplistic diagram of a proton, and I look at the surface of the proton, the surface is positively charged. So we have patches of positive charge on the proton, and these patches are going to repel one another because the distances are so small. It's just the size of the proton. So electrostatically, this proton should disintegrate. But we really know that the proton has a lifetime which is greater than the lifetime of our universe. So what is holding the proton together? It's a strong nuclear force. So in this case, the alpha nucleus is being held to the thorium nucleus because of the strong nuclear force, which is attractive in kind. And it sees a potential barrier. Now, let's find out the height of this barrier for the thorium nucleus. I would like to find out this height. Suppose the typical size of the nucleus R0 is 7.5 into 10 raised to power minus 15 meters. 7.5 femtometers. I would like to find out the height of this barrier. Could you please find out for me the height of this barrier from this expression?
So how does this show doubling?
I'll show it in a minute, right? Can you please find out the potential energy first? This object is 9 into 10 raised to power 9 Newton meter square per Coulomb square. करो हाथ से करोगे नहीं तो कैसे होगी फिजिक्स?
सर मैं conceptually understand.
Concept comes with
Yes.
the numerics, right? Otherwise it won't make sense.
सर ये वैसे R0 की वैल्यू हम डिफरेंशिएट करके निकाल सकते हैं।
R0 की वैल्यू
हम डिफरेंशिएट करके निकाल सकते हैं।
डिफरेंशिएट करके जीरो
डिफरेंशिएट करके
हाँ, लेकिन आपको उसका न्यूक्लियर फोर्स की फॉर्म पता होनी चाहिए, मैथमेटिकल फॉर्म।
लिमिट लगा के
नहीं वो हाइट तो चाहिए डिफरेंशिएट करके जीरो है।
डिफरेंशिएट किस फंक्शन को करेंगे?
ये VR
वो तो सिर्फ इलेक्ट्रोस्टैटिक पार्ट है।
यहाँ तक हम ये कुछ नहीं कर सकते लेकिन उससे यहाँ तक है।
इलेक्ट्रॉन वोल्ट्स में निकालें, इलेक्ट्रॉन वोल्ट्स में निकालें। क्यों जीरो रखेंगे? Why? You just have to plug in the value of Q1, Q2 and R to find out what the potential energy is. Why are you being so complicated? Why do you want to delve into the mathematics and do useless stuff? Just put in the values of the charges and find out what the potential energy is going to be. Electron volts में तो नहीं, ये into 10 plus 7, right? All right. So the answer is 35 mega electron volts. This height is 35 mega electron volts because you put Q1 is 90 times the charge on an electron, Q2 is 2 times the charge on an electron, R is this R0. So this barrier is of height 35 mega electron volts. But the alpha particles that you observe are only of energy 5 mega electron volts, and these alpha particles are coming from inside the nucleus. Do you understand the argument, the logic of the argument? This potential barrier is 35 mega electron volts, and the energy of the alpha particle that we are observing, which is coming outside the nucleus into our free classical world, is 5 mega electron volts only. It's just analogous to this situation. This barrier is higher than what this energy is. This energy is smaller than the barrier. In fact, it's about 1/7 of the height of the barrier. So how can this alpha particle surmount this barrier and come out while it preserves its low energy of 5 mega electron volts. Obviously, it cannot go up the barrier. It cannot go up the barrier because its energy cannot go up. If it goes up here, its energy increases to 35 mega electron volts. So when it comes down, it must have an energy of 35 mega electron volts. But the energy of this alpha particle is only 5 mega electron volt. So what is happening is that this alpha particle is just tunneling through this barrier. Alright? So it is tunneling that describes the behavior of the alpha particle. Another important aspect of natural radioactivity, and the sun makes its energy because of alpha decay. In the solar cycle, the proton cycle or the carbon cycle, alpha decays are important, and that's why the sun gives out energy. And when the sun gives out energy, it makes life possible on earth. So it is tunneling that is actually possibilizing or actualizing life on our earth. Now the one other interesting aspect is there is a certain tunneling probability that this alpha particle can tunnel outside the nucleus, and that tunneling probability we've denoted by T. It depends upon the height of this barrier, okay, and the length of this barrier, and the initial energy of the alpha particle. Okay. Now what's happening is that a large number of alpha particles in different thorium nuclei are bombarding with this barrier. They're constantly bombarding this barrier, and there is a small probability given by T that a single alpha particle can penetrate through tunneling and go out of the nucleus. Okay? So, and since the number of alpha particle that is bombarding the nucleus is very large, a large number of alpha particles they are issued. Now how do we calculate this tunneling probability? Okay, this tunneling probability, as we know, is proportional to exponent minus the length of the barrier divided by some penetration length, where this delta is given by h bar over square root of 2m v naught minus E, where v naught is the height of the barrier and E is the energy of the alpha particle. L is the length of this barrier.
I don't get.
I've done this in the previous class. Alright, so this is the tunneling probability. Now if there are a large number of nuclei that are bombarding this potential step, even if this tunneling probability is very small, say if it's of the order of 10 raised to power minus 15, a large number of alpha particles will actually come out. But the process is indeed probabilistic. Means an alpha particle strikes the barrier from the left, there's a probability that it will go out. Alright, so the process is indeed probabilistic. Can you please turn on the projector? And the tunneling probability, as you can observe, depends upon the initial energy of the alpha particle. So alpha particles with different energies will lead to different penetration lengths, and since this is exponential, it strongly depends upon delta. So different alpha particles with different energies will lead to different tunneling probabilities. And the number of decays per unit time is approximately given by number of alpha particles bombarding the potential step divided by time into the transmission probability. Do you agree with this? Well, because we can't really think of the alpha particles as bombarding the potential well, because the alpha, this is a very simplistic argument. Do you agree with this description? The number of decays per unit time, that is how many alpha particles that you observe per unit time, will depend upon how many alpha particles bombard this potential well per unit time, and what's the probability that each one of these alpha particles after bombardment can tunnel out of this potential well and become a free alpha particle and contribute to a radioactive particle. Okay, so you take the number of alpha particles bombarding the potential step per unit time and multiply it with the tunneling probability. So this will give you the number of decays per unit time. And since this is a probability, if you have 1 second, sometimes you will observe 1 decay, sometimes you will observe 5 decays, sometimes you will observe 10 decays, because this is just a probability. Alright, so radioactivity becomes a probabilistic affair. And it is quantum tunneling and the quantum nature of the tunneling that describes the probabilistic nature of radioactivity. Now what I have here is, alright, so can you find out the average time for a decay from this expression? What's the mean time for a decay? What's the average interval between two consecutive decays? It's just going to be the inverse of this, the time for a decay. And there's a large variety in the times for decays for different nuclei. I also have to show you a movie right at the end of this class. So what we observe here is there are different parent nuclei: polonium, radon, radium, different isotopes of radium and uranium. And the alpha particle that comes out from these parent nuclei, they have energies of the order of 4, 5, 6, 7, 8, 9 mega electron volts. Right? Much less than the 35 mega electron volt barrier. So these alpha particles are escaping from the nucleus because of tunneling. If you had no tunneling, if you had no quantum mechanics, in other words, if H bar, this H bar were 0, if H bar were 0, what would be the penetration length? 0, which means the wave function could not have penetrated into the classically forbidden region and no tunneling would take place. So a finite non-zero H bar makes tunneling possible. And H bar is small, that's why we don't see tunneling in our daily lives apparently. But H bar is non-zero, that's why quantum mechanics exists. And H bar is small, that's why we don't observe it so readily in our daily lives. So H bar is just fine-tuned. Okay? Every fundamental constant is fine-tuned. So this is the range of alpha particle energies in mega electron volts. And you will observe that the mean time for decay, which is just the inverse of this expression, is very diverse. Here you have 0.4 nanoseconds and here you have 6.5 billion years. So there is a huge range of decay times. And why is there a huge range of decay times? Because there's a huge range of tunneling probabilities. And why is there a huge range of tunneling probabilities? Because the tunneling probability depends exponentially on delta. And delta depends upon the difference between V0 minus E. And if E changes a little bit, this exponential factor changes by a very large amount. That is why we see a huge range of energies. In fact, as a homework, as a do-it-yourself exercise, what I would like you to do is, suppose my L is 10 nanometers, which is the length of the barrier, and my barrier V0 is 35. Alright, let's look at a simpler example. Is about 0.1 electron volts, and my energy is 0.05 electron volts. So calculate this exponential factor and the tunneling probability for these values, and then calculate for, you slightly change the energy of the alpha particle. You change it to say 0.04 electron volt. You will observe that the tunneling probability, since it's exponentially, it changes by a very large amount, by several orders of magnitude. So there is a very sensitive dependence upon the initial energy of the alpha particle. And that is why you see this huge range of tunneling probabilities, and hence the huge range in the mean time to decay, which is also called the half-life. Now we have a small demonstration for you of radioactivity. Can you please turn on the webcam? Okay, Ahmed. Alright, so what we have here, can you, oops. Tongs किधर है? दूसरा किधर है? Alright, so what we have here are some radioactive sources. So these yellow discs, they contain radioactive material. Alpha emitters, beta emitters, alright, and they are sealed and they are low activity, so they are safe to use. And one has to get permission from a regulatory authority to use these materials. But they are low activity, so they are harmless. Now, one of these materials we've placed, and of course, there's a radiation sign. You always have to observe the safety regulations. And what we see here is one of the sources is placed in a holder and it has a lead shield. Lights ठीक है? And it's continuously emitting radiation. And this radiation is being picked up by a tube, which is called a Geiger-Müller tube, a GM tube. When an alpha particle or a beta particle or a gamma ray photon enters this tube, it produces a flash. And that flash can also be heard. There's an audible click that you can hear if you remain silent enough. Can you hear these audible clicks? So these audible clicks are coming from from this device. Now this device is just counting the number of particles detected per unit time. It applies a very high voltage, about 900 volts, to the GM tube, and it's counting the number of counts or the number of particles or the number of decays per unit time. And we can observe these decays on the computer screen. So I turn off the lights so that you can see clearly. So what you observe on the computer screen is, I'm counting the number of counts in 1 second. How many particles reach the detector in 1 second? Sometimes 20 counts, I receive 20 counts per second. Sometimes I receive 25 counts per second, 30 counts per second. So I do not receive a constant number of counts per second, which means that this process is probabilistic. And I am plotting the number of occurrences versus the number of counts per second. So if I observe 30 counts per second, I observe it once, I get 1 here. If I observe 30 counts per second twice, this bar starts building up. So this is a kind of a histogram. So a histogram is gradually building up, and this represents the probabilistic nature of the radioactivity process. Even though I'm not using an alpha source here, but it vividly demonstrates that radioactivity is indeed a probabilistic process. So what I'm going to do now is, we have half an hour for the class. I'm going to keep this running, and we're going to see at the end of the class what this histogram is going to look like. So while we continue with the rest of the discussion, this experiment is going to run on its own. So now we have a radioactive source, a gamma source, a cobalt-60 isotope that is in front of you. It's emitting gamma ray particles, which are photons, nothing but photons, uncharged photons that are hitting on a Geiger-Müller tube, and the histogram is gradually building up. So that our remainder of the class isn't disturbed, I just turn off the audio while this experiment continually builds up. Okay, while we continue with our discussion.
So what's the y-axis?
The y-axis is the number of occurrences. It's a frequency histogram. How many times do I get 30 counts per second? How many times do I get 35 counts per second? And so on. Right? So this histogram is going to gradually build up. G.
Sir, how can you manage the number of alpha bombarding the potential? How can you manage?
So, what's your name? Saad has asked a very interesting question. How can we count the number of alpha particles bombarding the potential step? We can do that by having this term, this fraction can also be written as, if we have one alpha particle bombarding the step, how much time does the alpha particle takes to cover the length of the nucleus? So this fraction is the same as this fraction. I have one alpha particle bombarding the step. How much time does it take for one alpha particle to cover the distance of the nucleus? And this turns out to be equal to 1 over, what's the distance of the nucleus, or the length scale of the nucleus? It's 2 times R naught, the diameter of the nucleus. So what is R naught? I can put R naught as the R naught is just, so the time the alpha particle takes to cover the length of the nucleus, I call this tau, And what is this tau? Tau is just the distance to r naught divided by the velocity. So this fraction is equal to the speed of the alpha particle inside the nucleus divided by the typical diameter of the nucleus. So this is just a rough back of the envelope calculation. Okay, but this is how you can estimate this fraction. Now what we're going to do, we're going to look at another device that uses tunneling, a real device that uses tunneling. And that device is called a scanning tunneling microscope. This microscope was invented in the late 1980s, and the inventors of this microscope, Binnig and Rohrer, they were awarded the 1994 Nobel Prize in Physics for this invention. This device uses the effect of tunneling. Now what happens in a scanning tunneling microscope is that you have a solid surface, right? So what exists on the solid surface? Atoms. The solid surface is made up of atoms. So this is just a cartoon representation of a solid surface in which the atoms are bumping out. And now what you do is you have a metal tip, a tip of a metal, made up of a metal. If you have a metal, and you have electrons inside the metal. Do you have free electrons inside a metal? Yes. Can these electrons come out of the metal surface all by themselves? No. Why not? They have to overcome a work function. So these electrons are doomed to exist inside the metal. They cannot leave the surface of the metal. Alright? In other words, if you draw the potential landscape for these electrons, what is the potential landscape that these electrons see? It's going to be a zero potential energy and then a barrier of a certain height. So here the potential energy is zero, and here the electrons observe a certain barrier. And what's the height of this barrier? It's the work function, phi. So an electron that is here cannot go out of the barrier easily, because outside the metal you just have vacuum, and this vacuum goes to infinite length. Okay? So this is the potential landscape for electrons inside a metal. Now let's change the situation a little bit. How do I change the situation? Now I have a metal, and close to this metal I place a tip of another metal. And what I do is that I apply a potential difference between this metal and this metal. So this is a tip and this is my bulk metal. Now the potential difference is applied such that this tip is slightly positively charged with respect to this metal. Okay, I can take this to be ground, zero volts. So the potential energy is zero here. Now could you please tell me, how is this potential landscape going to be modified? Could you please draw the modified potential landscape for this configuration? First thing you should remember, if you have an electron inside the metal, the electron is at 0 volt. then the tunneling probability goes up even higher. Now there's one way of discussing this, and that is bringing the metal tip closer and closer to the bulk metal. But let's look at this situation in which the metal tip is kept at a certain height, and this metal tip is scanned over the surface of the metal. And wherever there is an atom, there is a bulge in the surface. Okay, there's a bulge in the surface. ठीक है, फिर flat है. And then there's an atom here, there's a bulge in the surface. Then it's flat. Then there's an atom, because the atoms are arranged at regular intervals. They're not squeezed together, and they're not touching shoulder to shoulder. The atoms are spaced apart at certain distances. That's what a crystal structure is. Now this tip is kept at a certain height. Let's call that height Z. When it's above, directly above an atom, what's going to happen is that the effective length L is going to decrease. And if this tip is positively charged, with respect to this solid surface, which is at ground potential, then electrons will favorably tunnel from this metal into the tip. Okay? And if I connect this tip to a sensitive ammeter, I can register a current. Now when this tip scans ahead and this tip moves on to this position, the distance from the solid increases, hence the current is going to decrease, and this current is being caused by tunneling electrons. So it's a tunneling current. And if I scan this tip along the surface, I will observe increase in current, decrease in current, increase in current, decrease in current, increase in current, decrease in current. That is why in 1988, when Binnig was experimenting with his microscope, he could not observe the current, he was just hearing the sound of, this current was being converted to a sound. So he observed the sound, ja, 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 and he called it a beautiful noise. Because this ja, every ja was an atom. So he looked at whenever the current peaked, he heard a da, and that da was one atom. So with the help of this atom, you can look at individual atoms. And in fact, you can look at the distribution of electrons. Because it's the electrons that are tunneling from the crystal to the metal tip. Why can't electrons tunnel from the metal tip to the crystal? Because this is at a lower potential for the electrons. So electrons favorably tunnel from the metal tip to the scanning tunneling microscope. And it is the scanning tunneling microscope that has resulted in revolutionizing physics. Especially it has blossomed the whole area of nanotechnology. Now you can see individual atoms, you can see individual molecules, you can see the distribution of electrons inside metals. So I'm going to show you a few beautiful pictures of crystal structures obtained from a scanning tunneling microscope. So this is not an artist's impression. This is a real image taken from a scanning tunneling microscope, of course falsely colored, but it's looking at the surface of copper, clean copper. Now what you observe is that the surface is not smooth. There are defects, there are steps, and you can see these ripples. These ripples are in fact the modulus squared of the wave function of the electron. Because wherever the modulus squared of the wave function of the electron is higher, higher will be the tunneling current. So the current goes up. So you can see these ripples. These ripples appear wherever there are defects or changes in the potential energy. Wherever there are discontinuities in the potential energy, ripples would appear. Here you would see a defect, an atom has gone missing. So you see these ripples, these circular ripples, like ripples in a water tank. Here there is a potential step, you will observe ripples. Here there is a potential depression, you will observe these ripples. These ripples are in fact standing waves. So you are directly imaging the modulus squared of the wave function of the electron. Alright. And this is the working principle of the scanning tunneling microscope. There is a tip that is moving, is scanning the surface, and these are tunneled electrons that are going from the solid to the metal tip. Whenever there is a bump, the atom is at an elevation, the tunneling current goes up. Here the tunneling current has gone down, it goes up again. And if you plot the tunneling current versus the scan of the tip, you will observe depressions and elevations, depressions and elevations. So you are mapping the topography, the contours on the surface of the solid. And each one of these bulges is one atom. So you can observe atoms. Atoms are tangible. They can be seen with, here we're seeing it then with the eye because the microscope is giving us a visual image. So atoms are real. Electron wave functions are real. Electron wave functions are discernible. They make sense. They make physical sense. Whatever we have been studying so far is tangible. It's very close to reality. It's not magical. It's not mystical. It's not religious. It's there. Some more images. Here another view of defects on a copper surface. As I mentioned, wherever you have a defect, you get these ripples. And these are standing waves of the electron wave function. Because there's a potential energy has been discontinuous, there are deflected electron waves. There are electron waves moving in the opposite direction. And when they interfere, they produce an interference pattern. And these are the interference patterns which are directly observable with the scanning tunneling microscope. Now here the red blobs, they are individual nickel atoms. One red blob is one nickel atom. And this blue blob is a xenon atom. It's a large atom that is binding to the surface of a nickel crystal. And this xenon is directly attaching itself to a nickel surface, to a nickel atom. So with the help of scanning tunneling microscope, if you're not looking at your mobile phones, you can observe that with the help of scanning tunneling microscopes, you can see processes as they happen on surfaces. You can see individual chemical reactions as they happen on surfaces. And you can look at the atomic level. And what you're actually seeing are electrons inside the atoms. Now here is a molecule of cesium and iodine atoms placed on a copper surface. This is one molecule, and these are cesium and iodine atoms. So you're directly mapping or imaging atoms, and you can observe that nature is the best artist, by the way. These are individual nickel atoms. These are platinum atoms, as seen by scanning tunneling microscope. These are gold atoms. Remember, this length is just 26 nanometers. This length is also 26 nanometers. So if I zoom in onto this area, this is 10 nanometers, this is 10 nanometers. And if I zoom in onto this area, this is about 4 nanometers, wide and 4 nanometers across. So you are observing individual gold atoms with the help of a scanning tunneling microscope. It's tunneling at its best. It's physics at its best. And these are modular squared of wave functions that are mapped directly with the scanning tunneling microscope. And you can make cool videos as well. So if you change the potential on the metal tip, you can get different amounts of tunneling, different amounts of current. And this is a sequence of images obtained with different potentials applied on the metal tip, positive potentials versus negative potentials. So you can make videos as well with the help of the scanning tunneling microscope. And the last thing I would like to mention is the beautiful work of quantum corals. In quantum corals, if you have the surface of the solid and there are atoms, and atoms bulge out somewhere, if the tip is brought really close to the bulge, to the atoms, and if it's brought really close, by van der Waals interaction, a chemical bond can be made between these bulging atoms and the metal tip. So this bulging atom, one or two of them will jump and stick to the metal tip. And now this tip is moved to a different location and it carries this metal with it. It's just like a helicopter that is taking its load from one point to another. And this metal, this atom that has been picked off from this location is being carried away by the metal tip. And then you change the potential on this metal tip. The interaction between this metal tip and the atom will decrease and this atom will fall down onto a new position. So you can pick up individual atoms on the surface of a solid by adjusting the potential on the metal tip and place those atoms wherever you like. You can make a painting. This stylus is your brush now. And this is your ink. The atoms become your ink. And you can place atoms wherever you like on the metal surface. So not only can you observe, you can also manipulate with the help of tunneling. And so this scanning tunneling microscope is not just a microscope, it's also a manipulator. It can make pretty patterns of atoms. And what I'm going to show you now are some of these pretty patterns that have been made with a scanning tunneling microscope. This is a copper surface and individual iron atoms have been placed on this surface in a hexagonal fashion here. This is a ring. Here you observe that the electron density, that is the modular square of the wave function, is bulging at the center. So these are different patterns that have been precisely engineered with the help of a scanning tunneling microscope. Before I show you the movie, because that's going to be the last thing in the class, let's have a look at what we observe from the Geiger counter. So this is the histogram that we obtained from gamma ray photons incident on a Geiger counter. As you observe, on average, there are about 35 counts per second because this histogram is peaking at around 35, but there are instances when one observes 30 counts per second, 25 counts per second, 20 counts per second, 40 counts per second, 45 counts per second, and so on. But this is the probabilistic nature of nuclear natural radioactivity. And this probabilistic nature is reflective of the probabilistic nature of of the quantum process. So I'm going to close this. In fact, those who are studying statistics, this is called a Poisson distribution. So I'm going to close this for the time being, and what I'm going to show you now is a movie. It's a 1-minute movie. This is the smallest movie ever made. Because in this movie, the actors, they're not human beings, they're not animals, but they are atoms. And this is a real movie that was made at IBM, in which a scanning tunneling microscope, a very large scanning tunneling microscope. If you want to look at small things, you need a large set of apparatus. That's very counterintuitive. But individual atoms of oxygen in carbon monoxide molecules, they were moved around in a sequence, and the scientists obtained 242 frames, static frames, and interlaced them in quick succession to give you the impression of a movie. So here is a movie in which the atoms are the actors, and it's the smallest movie ever made for the same reason. So let's look at the movie, but we also have to turn on the sound as well. On, okay. I turn off the Geiger counter. So please listen carefully. It's worth listening as well as watching. As you observe, in this video, each dot was a single oxygen atom in a carbon monoxide molecule, and these were 240 frames played out in quick succession. Tomorrow I am going to tell you that we can smell because of tunneling.